arithmetic shifting. In the unsigned numbers world, left shift is multiplication by 2. Just like that in base 10, left shift, or adding 0 from the right, is multiplication by 10. These two facts are things that we have already learned. I just remind you of those facts. If you don't fully remember how it works, you can go back to the bases lecture and base 2 lecture and take a look at it again. Right shift is division by 2. So we can use those shifts to perform arithmetic. We can maybe divide or multiply numbers by 2 or maybe by powers of 2 if we do those shifts many times. So let's look at two examples. Those two examples will be about signed numbers. We want to check if we can use shifts to perform signed arithmetic. We already know that it works in the unsigned numbers world. But what about the signed numbers? We have here two examples. One for shift left and one for shift right. And both of them will be for the same number, for the number FB, which is actually, when thinking about it in the 2's complement, is minus 5. So we try to shift left by 1. And we are going to get this result, F6, which is in 2's complement representation, minus 10, minus 0xa, which is minus 10 in decimal. So shift left actually multiplied by 2. Even though the number was negative, shift left somehow managed to understand it. He didn't really understand it, he just shifted bits. However, somehow it worked. Somehow magically it does work to shift left. However, we don't get such a good result with the shift right. We take a look at this number again, FB, and we shift right it by 1. We get this result, 7D, which is not even negative. This number is positive. We got a very large positive number when we tried to divide this negative number. So shift right didn't calculate the division correctly. Maybe to conclude, we can say that shift left works both with unsigned and signed numbers. However, it seems like shift right only works with unsigned numbers. It doesn't work very well with signed numbers. We should find some kind of alternative to the shift right instruction, at least in the signed arithmetic world. We want to be able to shift right negative numbers and somehow still get negative numbers as a result. And as you probably guessed, there are instructions for the signed case, for the case where we work with signed numbers. Just like almost everything in the x86 processor, there is always an alternative to the signed numbers. So how do these instructions work? I remind you that shift right inserts zeros from the left. Maybe we should insert ones instead when a negative number is given. And we will insert ones to preserve the sign bit of the original number. Previously, shift right just inserted zeros, and when we did that, we turned a negative number into a positive number, which is not the result that we want. Maybe if we insert ones from the left instead, we will get the right result. This is just some kind of a guess. So let's take a look at the shift arithmetic right instruction, which is also known as SAR. It shifts the bits of dest k bits to the right, and it does something else in addition. it inserts ones or zeros from the left according to the original sign bit of dest. That means that for positive numbers, we insert zeros, just like in shift right. But for negative numbers, we insert ones from the left. So this is a pretty smart instruction. It doesn't just pads with zeros from the left. It doesn't just push those zeros. It does something else. First, it takes a look at the most significant bit, the sign bit. And it just copies the sign bit. For positive numbers, it inserts zeros, and for negative numbers, it will insert ones. As we will see, and maybe you can even check it for yourself, this instruction actually works. You can actually take a negative number and shift arithmetic right that number by maybe one location, and it will correctly divide that number by 2. The dual instruction, shift arithmetic left, which has 2 arguments, dest and k, is just another name for the shift left instruction. We have already seen that shift left works correctly both with signed and unsigned numbers, so there is no need to do anything special with the shift arithmetic left. It is just another name for shift left, and you should pick the right name for the instruction, because those 2 names represent exactly the same encoding, according to what you want to do. It should just help you make your code more readable. It is not about the operation, because shift arithmetic left does exactly the same thing as shift left. In fact, those 2 instructions are exactly the same. They have exactly the same encoding. Let's look at an example for the shift arithmetic right instruction. We can see here 2 different pieces of code. This part of the picture corresponds to the topmost part, to this piece of code, and the bottom part of the picture corresponds to this piece of code. Let's try to understand the difference. In the first piece of code, we put this number inside AL, and this number is positive. However, in the second piece of code, we put this number inside, and this number is negative. Therefore, shift arithmetic right is going to do 2 different things in those 2 different pieces of code. In the first piece of code, shift arithmetic right is going to insert zeros from the right. Why? Because the most significant bit of the original number was 0. We can see it also here in the picture. This is the original number. The sign bit is here. It is 0. Therefore, shift arithmetic right is going to insert zeros from the right. In the second piece of code, the number that AL contains is negative. So AL is going to accept 1 from the right. Shift arithmetic right is going to insert the bit 1 from the right. This part corresponds to the second piece of code. We can see here the original number, which is negative, and the bit 1, which is inserted, and we get, for the first piece of code, this result, and for the second one, this result. I just want to show you, for example, that this kind of shifting to the right, with the part of inserting ones from the left, actually gives the right division result. Let's check it out. Let's try out the calculator. Okay, we move to binary mode, and I want to work with bytes. Now I have this number, 11001011. This is the number that we put inside AL in this piece of code, in the bottom piece of code. What does this number mean in decimal? It means minus 53. Remember this number, minus 53. Now let's check the number that we can see in the result. First, we move to binary. And now let's write that number. 1, 1, 1, 0, 0, 1, 0, 1. Now let's convert back to decimal. And we get minus 27, which is about half of minus 53. We can indeed see that the rounding doesn't go to the expected direction. Maybe you expected to see here minus 26, just like idiv is going to return. The idiv instruction will actually return minus 26 here. And this instruction, the shift arithmetic right, returns minus 27, which is pretty close to the correct result. Let's check, for example, what would have happened if we didn't use shift arithmetic right. If we used shift right, for example, then instead of this bit 1, we would have a 0. Let's check what happens when we have a 0. 0, 1, 1, 0, 0, 1, 0, 0. Okay, let's convert it to decimal. We can see that we have a really unrelated number. The original number was minus 53, and then we strangely got this result, which is not correct at all. So remember this. For unsigned numbers, you can use shift left and shift right. For signed numbers, you should use shift arithmetic right and shift arithmetic left. Roll and roar. Those two instructions allow to rotate left or rotate right. For example, rotate left, dest, k. This instruction rotates the bits of dest k times to the left. The other instruction, rotate right, dest k, rotates the bits of dest k times to the right. You'll probably not be too surprised about what I'm going to say about the carry bit. The carry flag contains a copy of the last bit which was shifted from one end to another. Don't worry, we are soon going to see it in a picture. Some constraints about this or those two instructions. K should be one of the following: a small number, which means not bigger than the size of a byte, from 0 to FF, or the CL register. K cannot be anything else. For example, it cannot be BH, BL, DH, and so on. It can only be a small number or the CL register. Let's look at an example. Here we move this value inside AL, and then we rotate right AL by 1. So what actually happens here? Originally we have this value inside AL, and the rotate right instruction rotates all the bits one slot to the right. So this bit 0 moves right to this new location, and the bit 1 moves here, and so on. The interesting part is the last bit, the leftmost bit or the least significant bit. Two things happen to this bit. First, it is copied to the carry flag, and at the same time it moves all the way to the most significant bit. Finally, we get that this bit 0 moves here, and this bit 1 moves here, and the bit 0 here moves to its new location here. This 1 bit moves here, and this bit 1 moves all the way to this new location, and it is also copied into the carry flag. The rotate left and rotate right instructions are really useful because they don't waste bits, they don't delete any bit. You can see that all the bits are preserved. No new bits are stuffed from the left or from the right, and the bit that exits the boundary comes back from the other side. I also want to say that if we use rotate left, then the bit from the left would be copied to the carry flag, and it will also move to the right. Summary. We have learned about the logical instruction NOT, AND, OR, and XOR. Those instructions correspond to the Boolean operators we have already learned about in the Boolean algebra chapter. We have also seen some bit shifting instructions which allow us to somehow mix the bits, because the NOT, AND, OR, and XOR only allow us to work with parallel bits. We have to shift bits around to be able to do more complicated things. So first we've seen shift left and shift right, which are mostly about simple bit shifting. Then we've seen arithmetic shifting kind of instruction, shift arithmetic left and shift arithmetic right. Those two instructions work very well with signed numbers, mostly the shift arithmetic right. Shift arithmetic left is just like shift left. Those two instructions are the same. Shift arithmetic right has the feature of choosing between inserting zeros or inserting ones from the left. Finally, we have seen those two last instructions, rotate left and rotate right. The rotating bits instructions have the very special feature of preserving the bits, which means that no bits are deleted. The last bit that falls from the right just goes all the way back to the leftmost bit. So it's really nice. They are sometimes very useful. That's it for today. We are not going to have exercises for this lesson because we still have to learn some more practical ways of using those instructions. See you next time.